All right, let's dive into a system design interview classic. How would you build a content delivery network, a CDN, from the ground up? This is one of the absolute cornerstones of the modern internet, so let's break it down. So, what's the core problem we're even trying to solve here? Well, imagine your company's server is in, say, Virginia. What happens when someone in Tokyo wants to see your website? You run into a little unavoidable problem called the laws of physics. Data can only travel so fast, and that round trip across the globe creates lag, or what we call latency. And that's exactly where a CDN comes in. You can think of it like a global network of mini warehouses for your website's content. Instead of everyone having to go all the way back to Virginia, they can just grab a copy from a local warehouse nearby. It's a super smart, distributed caching layer that brings content closer to your users, and that makes everything feel way, way faster. Okay, so if we were going to build one of these massive systems, where would we even start? Here's our game plan. We're going to walk through this just like you would in a real system design interview from the ground up. First things first, before we can design anything, we have to know exactly what we're building. We need to scope the problem by laying out our requirements, both functional and non-functional. So on the functional side, what does this thing actually have to do? Well, it needs to grab content from the original source. It has to serve that content when users ask for it. It needs a way to get the content out to all of its proxy servers. And it's got to be smart, right? It needs to search its own cache, update things when they change, and of course, get rid of old, stale data. And then there are the non-functionals, and for a CDN, these are everything. Performance is number one. Low latency is the whole reason we're building this. It has to be highly available. It can't go down, ever. It needs to be massively scalable to handle huge spikes in traffic. And of course, it has to be a fortress, totally reliable and secure enough to fend off things like huge DDoS attacks. All right, requirements are locked in. Now we get to the fun part, sketching out the high-level architecture. What are the main building blocks of our CDN? First up, you've got the routing system. This is the brain of the operation, the air traffic controller. Its entire job is to look at an incoming request from a user and decide, okay, out of my thousands of servers around the world, which one is the absolute best one to handle this request right now? Next, you have the proxy servers themselves. These are the workhorses, the boots on the ground at the very edge of the network. These servers are what make a CDN feel so incredibly fast because they're physically close to you and they're serving that content directly from super fast storage, like RAM. But wait, how does the content even get to all those proxies in the first place? Well, that's the job of the distribution system. Think of it as the CDN's internal logistics and shipping network. Its whole purpose is to efficiently get content from the original source out to all those global locations. And finally, you have the origin servers. This is where it all begins. It's the one single source of truth for your content. In fact, everything the CDN does is basically designed to act as a giant shield to protect this origin server from getting hammered with requests. So let's put all those pieces together. What's the actual workflow look like? It's a pretty cool orchestrated dance. The origin publishes its content to the distribution system. That system gets it out to the proxies. Then, when your browser wants something, it first asks the routing system, hey, where should I go? The routing system points it to the best proxy, and boom, your browser grabs the content directly from that nearby server. Simple, fast, and efficient. Okay, now we're going to zoom in on one of the most critical design choices you have to make when building a CDN. How exactly does the content get onto those proxy servers to begin with? And it really boils down to this classic trade-off, push versus pull. In a push model, the content owner proactively uploads their files to the CDN. This is awesome for stuff you know will be popular, like a big software update or the main video on your homepage. The opposite is a pull model. Here, the CDN has no idea the content even exists until the very first user asks for it. At that moment, the proxy pulls it from the origin and saves a copy. This is perfect for things like user-generated photos on a social media site where you have millions of files and no idea which one will be requested next. So why is this push versus pull choice so important? Well, it's because internet content almost always follows what we call a long-tail distribution. You have a few massive hits that everyone wants, and then this incredibly long tail of millions of items that are almost never requested. A pure push model would be super wasteful, filling caches with stuff nobody wants. This is why a hybrid or layered pull model is so powerful. It naturally adapts to what's actually popular right now. Okay, so our content is cached all over the world. But here's the magic question.
How does your computer in Sydney know to connect to the server in Sydney and not the one in Frankfurt? How do we find the nearest server?
And the answer is pretty fascinating, because nearest doesn't just mean geographically closest. That routing system is constantly crunching numbers. It's looking at network distance, like how many hops it takes for data to get there, and the available bandwidth on that path. But it's also looking at the health of the servers themselves. Is that Sydney server getting slammed with requests right now? You know what? It might actually be faster to send you to a less busy server in Melbourne. So how do they pull this off? There are two really clever techniques used here. The first is DNS redirection. When your computer asks for a website's IP address, the CDN's smart DNS server looks at where you are and gives you the IP of a server that's close to you. The other method, which is even cooler, is Anycast. With Anycast, a whole bunch of servers all over the world announce the exact same IP address. Then, the internet's own core routing protocol just magically sends your traffic to whichever server is closest from a pure network perspective. It's brilliant. All right, let's take a step back. We've designed this whole system, from the components to the caching and routing logic. It's time to grade our own homework. Do we actually meet those critical non-functional goals we set out at the very beginning? So, how did we do? Well, for performance, check. By distributing those proxy servers everywhere, we've crushed latency. Availability? Yep. With thousands of servers, there's no single point of failure. If one data center has a problem, we just route traffic somewhere else. And what about scalability? Absolutely. This design is built to scale horizontally. If you need more capacity in Europe, you just spin up more edge servers. Simple as that. And that really is the heart of it. A well-designed CDN isn't just a performance hack. It fundamentally changes the economics of delivering content at a global scale. By bringing content closer to users, you slash your bandwidth costs, and you build a system that can grow almost infinitely. It's truly a pillar of the modern internet. So we've designed a powerful CDN for the internet of today. But that leaves us with a really interesting question to chew on. As the edge gets smarter and we start running actual code out there, not just caching files, what does the CDN of tomorrow look like? How will these fundamental principles have to evolve? That's something to think about.